Taiwan Strait, 1958. A Chinese pilot squeezed the trigger, launching his brand-new PL-2 air-to-air missile at a Taiwanese F-86 fighter just seconds away. The missile ignited and immediately tumbled out of control, spiraling wildly before its motor burned out and it fell harmlessly into the sea. The pilot watched in disbelief as his target escaped unscathed. Within weeks, Chinese commanders would discover their copy of America's legendary Sidewinder missile had a success rate of barely 15%, and even that was optimistic. This is the story of how China tried to steal one of the West's most successful weapons and created a missile that was more dangerous to launch than to be targeted by. The missile that changed air combat. The AIM-9 Sidewinder revolutionized aerial warfare when it entered service with the U.S. Navy in 1956. Before the Sidewinder, shooting down enemy aircraft required pilots to maneuver into gun range and achieve the split-second precision needed for bullets to hit a fast-moving target. It was an art requiring exceptional skill, perfect timing, and often suicidal courage to close within effective range of an opponent's guns. The Sidewinder changed everything. This heat-seeking missile allowed pilots to engage targets from beyond visual range, firing from positions where enemy guns couldn't reach them. The missile's infrared seeker detected heat from enemy engines, guiding itself autonomously toward the target without further pilot input. Once launched, the Sidewinder became an independent hunter, tracking, adjusting, and pursuing its target with relentless precision. The weapon's effectiveness was proven dramatically in September 1958 during the Second Taiwan Strait Crisis. Chinese MiG-17 fighters engaged Taiwanese F-86 Sabres in aerial combat over the strait, separating mainland China from Taiwan. The Taiwanese aircraft were equipped with early Sidewinder missiles, while the Chinese pilots had only guns. The result was a massacre. Taiwanese pilots shot down multiple Chinese aircraft without a single loss, demonstrating the overwhelming advantage that effective air-to-air missiles provided. For Chinese military leadership, this defeat was both humiliating and enlightening. The Sidewinder represented exactly the kind of technological superiority that allowed smaller, less numerous forces to dominate larger adversaries. If China could acquire Sidewinder technology, they could reverse the tactical situation and potentially dominate Asian airspace. Fate, or rather incompetence, provided the opportunity. During the 1958 Taiwan Strait engagements, several Sidewinder missiles were fired at Chinese aircraft but failed to detonate. One missile lodged intact in a Chinese MiG-17 that managed to limp back to base despite having a live missile stuck in its fuselage. The missile was carefully removed and immediately shipped to the Soviet Union, China's ally at the time, where Soviet engineers could examine this prize of Western technology. What followed was one of history's most successful reverse engineering efforts and one of its most catastrophic failures. The Soviets successfully copied the Sidewinder, creating the K-13, NATO designation AA-2 Atoll, which became the Soviet Union's primary air-to-air missile for decades. They achieved this by meticulously examining every component, understanding the underlying principles, and developing manufacturing processes capable of replicating the critical systems. China attempted the same process, but with vastly different results.
The anatomy of deception. Chinese engineers received detailed technical information about the Sidewinder from Soviet sources, drawings, specifications, test data, and manufacturing guidance. The Soviets having successfully copied the missile themselves, generously shared this intelligence with their Chinese allies. Chinese leadership was ecstatic. With Soviet assistance, surely China could rapidly field its own Sidewinder equivalent and close the tactical gap that had proven so costly over Taiwan. The program, designated PL-2, Pili 2, meaning Thunderbolt 2, was assigned to the newly established China Airborne Missile Research Institute in 1958. Chief designer Liang Dongsheng, a Soviet-trained engineer who had worked on various Chinese aircraft programs, was placed in overall charge. The directive was clear: produce a Chinese version of the Sidewinder capable of equipping the People's Liberation Army Air Force as quickly as possible. Liang examined the Soviet technical data with growing concern. The Sidewinder, despite its apparent simplicity, just a tube with fins, a seeker head, a warhead, and a rocket motor, was actually an exquisitely sophisticated system requiring precision manufacturing and technologies China had limited experience with. The infrared seeker. The Sidewinder's seeker detected infrared radiation from target aircraft engines, tracked the heat source, and generated steering commands to guide the missile. This required sensitive infrared detectors, lead sulfide cells cooled by compressed gas, sophisticated optical systems to focus and direct infrared energy, gyroscopes for stabilization, and analog computing circuits to process signals and generate guidance commands. Each of these elements represented technologies at the frontier of 1950s capabilities. The control system. Keeping the missile stable in flight while responding to guidance commands required control surfaces, the fins, actuators to move those surfaces with precision, and a power system to operate the actuators. The Sidewinder used a miniature gas turbine powered by compressed air to generate electricity and hydraulic pressure. This system was remarkably sophisticated, cramming power generation into a package small enough to fit in a missile body just 5 inches in diameter. The fuzing system. The warhead had to detonate at exactly the right moment, close enough to damage the target but not so late that the opportunity was missed. The Sidewinder used a combination of proximity fusing, detecting when the missile was near the target through radar or infrared sensors, and contact fusing, detonating on physical impact. This system required split-second timing and reliable electronics operating under extreme acceleration, vibration, and temperature variations. The rocket motor. The motor had to provide sufficient thrust to accelerate the missile to supersonic speeds quickly, maintain that speed through the flight, and do so with consistent performance across wide temperature ranges. The solid propellant chemistry, grain geometry, and nozzle design were all critical to achieving the required performance. Every subsystem presents challenges, Liang told his team during initial planning meetings in 1959. The Soviets succeeded because they had industrial capabilities we lack. They could manufacture precision gyroscopes, produce sensitive infrared detectors, and build miniature gas turbines. We're attempting the same tasks with less sophisticated equipment, less experienced workers, and more limited access to specialized materials. We'll need to make compromises. These compromises, driven by China's limited industrial capabilities and political pressure to show rapid progress, would doom the PL-2 to become one of the most unsuccessful weapons in aviation history.
The manufacturing catastrophe. Production of PL-2 components began in 1960 across multiple Chinese factories, each struggling with technologies they had minimal experience with. Infrared seekers. The seeker head was perhaps the most challenging component. Chinese facilities attempting to manufacture lead sulfide infrared detectors discovered that their production processes resulted in inconsistent sensitivity. Some detectors worked adequately, others were nearly blind to infrared radiation. The cooling system, using compressed gas, required miniature valves, regulators, and plumbing that Chinese precision machining couldn't reliably produce to required tolerances. The optical system required precision ground lenses that Chinese optical facilities struggled to manufacture with adequate quality. Our seeker heads show enormous performance variation, reported the Seeker production supervisor in 1961. Some can detect target aircraft at the required ranges. Others can barely see anything unless the target is directly ahead and very close. We don't have adequate quality control to distinguish good seekers from bad ones during manufacturing, so defective units are getting installed in missiles. Those missiles will be essentially blind when launched. Guidance and control. The gyroscopes required for missile stabilization and the actuators needed to move control surfaces both demanded precision manufacturing China couldn't consistently achieve. Gyroscopes were unreliable, drifting unpredictably and causing guidance errors. Actuators were sluggish and imprecise, meaning the missile couldn't respond quickly enough to steering commands. And the miniature gas turbine that powered these systems was plagued by failures, starting unreliably, running inconsistently, and sometimes failing completely during flight. Warhead and fusing. The proximity fusing system, which detected when the missile was near its target, proved beyond Chinese electronics capabilities to manufacture reliably. Many PL-2 missiles were fitted with contact fusing only, meaning they had to physically strike the target to detonate. This dramatically reduced effectiveness, since even slight trajectory errors would cause the missile to miss by feet rather than close enough for proximity detonation to destroy the target. Rocket motors. The solid propellant motors showed enormous performance variations due to inconsistent propellant chemistry and poor quality control. Some motors produced adequate thrust and burned smoothly. Others generated insufficient thrust, burned erratically, causing the missile to tumble, or occasionally exploded during launch due to cracks in the propellant grain that created dangerous pressure spikes. Each of these problems was well known to engineers and supervisors. Technical reports documented the deficiencies, quality control testing revealed failure rates, and engineers repeatedly warned that the missiles being produced weren't combat effective. But political pressure demanded continuing production. We cannot admit that we're unable to manufacture missiles the Soviets successfully copied. This would suggest Chinese technical inferiority. We will proceed with production using available components, and field experience will drive improvements. This decision to field missiles known to be defective because admitting inadequacy was politically unacceptable would directly lead to Chinese pilots' deaths.
The field testing disaster. Limited flight testing of PL-2 missiles began in 1962, with the weapons fired from J-5 fighters, Chinese-built MiG-17s, at drone targets. The results were catastrophic. Of the first 20 missiles fired under carefully controlled test conditions, 6 failed to launch, with rocket motors igniting but immediately shutting down. 4 tumbled immediately after launch due to control system failures. 3 exploded shortly after launch, with 1 damaging the launch aircraft. 5 flew relatively straight but showed no indication of tracking targets, suggesting seeker failure. 2 appeared to track targets initially, but then lost lock and flew wild. 0 successfully intercepted their targets.
We have a 0% success rate, the test director reported in disbelief. Not a single missile has functioned as designed. Most fail catastrophically within seconds of launch. The few that achieve sustained flight show no tracking capability. We're not even close to having a working weapon system. Extensive analysis of the failures revealed systemic problems. Seeker failures. The infrared seekers were simply too inconsistent to work reliably. Even those that functioned during ground testing often failed when subjected to vibration, acceleration, and temperature variations of actual flight. The optical components came out of alignment, the infrared detectors lost sensitivity, and the cooling systems leaked or failed. Guidance failures. The guidance and control systems couldn't keep missiles stable or respond quickly enough to steering commands. The gyroscopes drifted unpredictably, the actuators were too slow and weak, and the power systems were unreliable. The result was missiles that couldn't track targets even when the seekers worked. Structural failures. Several missiles broke apart in flight due to structural weaknesses. The thin aluminum bodies weren't strong enough to withstand aerodynamic loads during high-speed flight, causing catastrophic failures that sent debris through the air dangerously close to launch aircraft. The motors failed. The rocket motors were unreliable nightmares. Some burned too hot, destroying internal components. Others burned unevenly, causing wild gyrations. A few exploded, and one particularly horrifying incident involved a motor that burned through the missile body, sending a jet of flame toward the launch aircraft that nearly caused the pilot to eject. The PL-2 is not just ineffective, it's dangerous, the test report concluded. Pilots launching these missiles risk being killed by their own weapons. The failure rate is so high that PL-2-equipped aircraft are less combat effective than aircraft carrying only guns. We strongly recommend suspending the program until fundamental design and manufacturing problems can be resolved.
The pressure to deploy. The test director's recommendation to suspend the program was ignored. Chinese military leadership, facing continuing tensions with Taiwan and increasingly strained relations with the Soviet Union, wanted domestically produced air-to-air missiles regardless of their effectiveness. The political investment in the PL-2 program was too great to admit failure. In 1965, PL-2 missiles began entering service with PALAF fighter units, despite the weapon's demonstrated unreliability. Pilots were told the missiles were being improved through ongoing development and that early problems had been resolved. This was, at best, wishful thinking, and at worst, deliberate deception. The missiles entering service were fundamentally the same as those that had failed catastrophically during testing. We were issued PL-2 missiles and told they would give us capability against Taiwanese aircraft, recalled a Chinese pilot years later. But we weren't confident. We'd heard rumors about test failures, and the weapons looked crudely made compared to the aircraft systems we were used to. Loading them felt like attaching bombs that might go off randomly, rather than precision weapons we could rely on. The pilots' concerns proved well-founded. During engagements over the Taiwan Strait in the mid-1960s, PL-2 missiles were fired dozens of times with minimal success. The exact success rate remains classified, but estimates based on fragmentary reports suggest perhaps 10 to 15% of missiles launched achieved anything resembling effective tracking, and far fewer actually destroyed targets. Most missiles simply failed in the ways that testing had already revealed. Launch failures where motors ignited but didn't produce sufficient thrust. Immediate tumbling after launch due to control failures. Seekers that never locked onto targets or lost lock immediately. Guidance failures that sent missiles on wildly erratic trajectories. Warheads that failed to detonate even when missiles passed close to targets.
In several horrifying incidents, PL-2 missiles endangered or damaged the launch aircraft. A motor explosion during launch that sent fragments through the wing of the carrying aircraft, forcing an emergency landing. A missile that separated from its launch rail but immediately turned back towards the launch aircraft due to guidance failure, narrowly missing as the pilot maneuvered desperately. A seeker cooling system leak that released compressed gas into the cockpit, nearly suffocating the pilot. Fighting with PL-2s was worse than fighting with guns only, one pilot admitted. Guns were reliable. You knew what they would do. The PL-2 was completely unpredictable. You never knew if it would work, fail harmlessly, or try to kill you. We started treating them like bombs, something dangerous we had to carry that might go off at the wrong time.
The human cost and cover-up. The exact number of Chinese pilots killed or injured by PL-2 failures remains unknown and will likely never be officially acknowledged. The catastrophic failures were classified, incidents were attributed to other causes, and the extent of the weapon's inadequacy was buried in secret reports. But the human cost extended beyond physical casualties. Every pilot who flew with PL-2 missiles carried the knowledge that their weapons were unreliable and potentially dangerous. This affected their combat effectiveness, their confidence, and their trust in the equipment and leadership that provided such inadequate weapons. Captain Wang Guohua died in 1966 when a PL-2 missile exploded during launch, sending fragments through his J-5 fighter's fuel tank. The aircraft exploded seconds later, killing Wang instantly. Official records attribute his death to combat operations, with no mention that he was killed by defective Chinese equipment rather than enemy action. His family was never told the truth about how he died or that the weapon that killed him had been known to be dangerously defective before it was ever issued to operational units. Wang's story was repeated multiple times during the PL-2's brief operational career. Each casualty represented not combat losses, but victims of a system that valued political objectives over pilot safety, that deployed known defective weapons rather than admit technical inadequacy, and that covered up failures rather than learning from them. The psychological toll on surviving pilots was significant. Trust in equipment, critical for effective combat operations, was severely damaged. Pilots became reluctant to use the missiles they were issued, preferring to rely on guns despite the tactical disadvantages. Some pilots reportedly jettisoned PL-2 missiles before engaging enemies, believing they were safer without weapons that might malfunction catastrophically. "We lost faith in our own equipment," recalled one veteran. "If they would issue us missiles that they knew were defective, what else couldn't we trust? The aircraft maintenance? The ejection seats? Every system became suspect. That uncertainty was almost as dangerous as enemy fire."
The gradual improvement. The PL-2 was quietly phased out of frontline service by the early 1970s, replaced by improved versions, PL-3 and PL-5, that incorporated lessons from the initial failure and benefited from incremental improvements in Chinese manufacturing capabilities. These later missiles were more reliable, though still far from matching the effectiveness of contemporary Western weapons. The improvement came through patient, systematic development rather than attempting shortcuts. Material science, Chinese metallurgy, electronics, and chemicals industries gradually improved, producing materials with more consistent properties and better performance characteristics. Manufacturing precision, machine tools improved, workers gained experience, and quality control systems were strengthened, resulting in components manufactured closer to specifications. Engineering understanding. Chinese engineers developed deeper understanding of missile guidance, propulsion, and warhead design through accumulated experience, rather than just copying foreign examples. Quality systems. Recognition that fielding inadequate weapons was worse than admitting technical limitations led to more rigorous testing and willingness to reject defective components. By the 1980s, Chinese air-to-air missiles had improved significantly from the PL-2's dismal standards. The PL-5, while still inferior to contemporary American Sidewinders, was at least reliable enough to use in combat without endangering the launch aircraft. Chinese pilots could finally trust that their missiles would probably work when fired, a basic standard that should never have been in doubt. But this improvement came through the same patient development that China tried to shortcut with the PL-2. The lesson that stolen technology without the industrial capability to produce it reliably results in dangerous failures took China 15 years and multiple casualties to learn.
The broader implications. The PL-2 disaster was part of a pattern in Chinese military-industrial development during the 1960s to 1970s. Identify successful Western weapon, acquire technical data through espionage or allies, attempt production without adequate industrial capabilities, discover that copies don't work reliably, deploy defective weapons anyway due to political pressure, discover failures during operational use, sometimes with lethal consequences, cover up failures while gradually improving through patient development, eventually achieve adequate capability years or decades later, claim success while never acknowledging the failures. This pattern reflected fundamental problems in China's approach to military technology during this period, attempting to leapfrog developmental stages through copying rather than building genuine capability, allowing political considerations to override technical reality, and valuing appearance over functionality. The Sidewinder that China tried to copy evolved through continuous improvement over decades. The AIM-9B from 1958 was followed by the AIM-9D, E, J, L, M, and X variants, each incorporating lessons learned from operational use and advances in technology. By the time Chinese missiles finally achieved basic reliability in the 1980s, American Sidewinders had advanced 3 or 4 generations beyond what China was struggling to copy.
The enduring reality. Today, China produces competent air-to-air missiles, including the PL-10 and PL-15, which represent genuine indigenous development, informed by decades of accumulated experience. These weapons demonstrate that China eventually developed the industrial capabilities and engineering expertise necessary for effective missile production. But this capability came through patient, systematic development over decades rather than through the shortcuts attempted with the PL-2. Chinese engineers had to build the industrial ecosystem, the materials science, precision manufacturing, quality control systems, and accumulated expertise that made reliable missiles possible. This couldn't be stolen or copied, but had to be earned through long-term investment in fundamentals. The PL-2 remains a largely forgotten embarrassment in Chinese military history, rarely mentioned even in internal documents. But those who flew with the missiles, who saw them fail catastrophically, or who lost friends to defective weapons, remember. They carry the knowledge that China once fielded weapons so inadequate that pilots were safer without them, that political objectives overrode safety considerations, and that failures were covered up rather than acknowledged. For the families of pilots like Wang Guhua, killed by defective Chinese weapons rather than enemy fire, the PL-2 represents a betrayal, leaders who valued political face over pilot safety, who deployed weapons they knew were dangerous, and who covered up deaths that were entirely preventable. These casualties deserved better than they received from a system that treated them as expendable in service of political objectives.
The PL2 story stands as a cautionary tale about the costs of attempting technological shortcuts, of allowing politics to override engineering judgment, and of deploying equipment that looks capable but fails when lives depend on it. The lesson that technological capability must be earned rather than stolen, and that patient development produces better results than desperate copying, remains relevant decades later as nations continue grappling with the temptation to shortcut development through espionage and reverse engineering. The Sidewinder missile that inspired the PL2 continues in service today in evolved forms, more than 65 years after the original entered service. The PL2, which attempted to copy it through theft and shortcuts, lasted barely a decade before being withdrawn as too defective to use. The contrast illustrates the difference between genuine engineering excellence and attempts to fake it through copying. One produces weapons that endure and inspire confidence. The other produces weapons that fail catastrophically and kill those who depend on them.